Good morning, everyone. Today, I will be presenting about grid-forming inverters and their critical role in modern power conversion systems, or PCS. This presentation will cover the differences between PCS and PV inverters, inverter topologies, operating modes, grid-forming functions, fault responses, and why these technologies are essential for the future of power grids. Let's begin. Developed and presented by PEC Technology. First, let's compare a PV inverter with a power conversion system. A PV inverter simply converts DC from solar panels into AC and is designed to maximize solar output. However, it can only operate in two quadrants 1 and 4, which limits its flexibility. On the other hand, a PCS is a bidirectional inverter. It can convert DC to AC and also AC back to DC, supporting battery integration. This allows full 4-quadrant active and reactive power control, making PCS a much more advanced and versatile system. Now, the PCS has several key features that make it essential in modern energy systems. First, it supports bidirectional power flow, meaning it can both charge and discharge. Second, it works in both on-grid and off-grid modes, giving flexibility for different applications. Third, it enables active and reactive power control, helping stabilize voltage and energy flow. Fourth, it is equipped with intelligent control, typically managed by a battery management system and an energy management system. And finally, it offers high efficiency, often between 95 and 99% depending on design. Now let's look at inverter topology. Topology refers to the structure and arrangement of power components and switching devices. In other words, how DC is converted into AC. There are two major topologies used in industry, the 2-level inverter and the 3-level inverter. A 2-level inverter has a simple design and lower cost, which makes it attractive. However, it comes with disadvantages: higher switching losses, more harmonic distortion, and therefore limited use in high-power or complex grid applications. On the other hand, the 3-level inverter addresses many of those limitations. It has lower switching losses, higher efficiency, and produces higher quality output with less harmonic distortion. It also requires a smaller output filter. Of course, it is more complex and more expensive. But because of its performance, the 3-level inverter is widely used in high-power industrial applications. Grid-forming inverter. Now we come to the heart of this presentation, the grid-forming inverter, or GFMI. Unlike traditional grid-following inverters, which depend on an existing grid signal, a GFMI acts as a voltage source for the grid. It creates and maintains grid voltage and frequency on its own, providing a fundamental reference for the system. Now, let's look more closely at what a grid-forming inverter, or GFMI, really is. Unlike a grid-following inverter, GFMI acts as a voltage source for the grid. It provides the fundamental reference for both voltage and frequency. This means it is capable of creating and maintaining grid voltage and frequency entirely on its own, even without support from the utility grid. To better understand the difference, let's compare grid-forming and grid-following inverters. A grid-forming inverter controls as a voltage source, while grid-following operates as a current source. Grid-forming creates its own voltage and frequency reference, whereas grid-following must follow the grid's existing reference. Another key difference is black start capability. Grid-forming inverters can restart the grid after a blackout, but grid-following inverters cannot. In terms of control, grid-forming uses voltage-frequency control with droop characteristics, while grid-following relies on PLL-based current control. Finally, grid-forming inverters can work in grid-tied, islanded, or off-grid modes. Grid-following inverters, however, can only operate when tied to the grid. In microgrid applications, PCS plays a vital role. It combines both grid-tied and off-grid capabilities, enabling flexible operation. But for off-grid functionality, a grid-forming inverter is required to establish and maintain the local grid. In fully off-grid mode, the PCS operates independently from the main grid. Here again, the grid-forming inverter is essential. Without GFMI, the system cannot form the local grid voltage and frequency on its own. It's also important to compare the behavior of inverters with traditional generators. An inverter operating in grid-forming mode has fundamentally different characteristics compared to a synchronous generator. Instead of relying on mechanical inertia, it uses control algorithms to emulate similar behavior. This brings us to the concept of the virtual synchronous generator, or VSG. VSG emulates the behavior of a synchronous generator entirely through software. It allows the inverter to respond to imbalances between generation and load with virtual inertia. The higher the virtual inertia, the shallower the frequency drop and the slower the rate of change of frequency. To support stability, droop control is applied. It involves both frequency and voltage control. For frequency, droop control provides virtual inertia, damping, and governor-like action. For voltage, it functions like an automatic voltage regulator, stabilizing output voltage. We often represent this behavior using FP droop and VQ droop curves. One of the key roles of a grid-forming inverter is to support grid resilience. During faults or disturbances, the inverter must respond quickly and safely to protect the system and maintain stability. During a voltage drop, whether minor or major, the inverter limits output current by reducing voltage. This protects the inverter, prevents overcurrent trips, and helps stabilize the grid, especially during large current spikes. In a severe fault scenario, such as a short circuit, there are two possible cases. First is the self-clearing fault, where grid impedance recovers on its own. In this case, the inverter increases current to support recovery, then reduces current again to maintain stability. In the second case, the fault does not clear, meaning grid impedance remains near 0 ohms. Here, the inverter must act quickly to limit fault current and disconnect. This rapid disconnection protects equipment and ensures system safety. Another critical feature of GFMI is black start. This is the ability of the inverter to re-energize a grid from a complete blackout without relying on external power. In the startup phase, the inverter operates in island mode. It establishes a low fixed voltage, for example, 50 volts AC line to neutral, as the first step of grid verification. In the walk-in phase, the inverter gradually ramps up voltage and controls frequency towards the target set points. The system uses voltage control with QU and frequency control with PF to stabilize. Finally, in the running phase, the black start process is complete. The inverter has formed a stable grid, and the system is now ready to connect additional islanded inverters and loads. GFMI also enables seamless transition between grid-connected and islanded modes. When the circuit breaker opens, the grid-forming inverter immediately forms and maintains a stable island grid, ensuring uninterrupted power supply. GFMI is not just an option, it is a necessity for the future grid. As more renewable energy enters the system, traditional synchronous generators are being replaced. GFMI enables reliable, resilient, and renewable-based power systems. In the future power grid, GFMI will play a central role. It can form and maintain voltage and frequency, enable high renewable penetration, provide black start and seamless transition capabilities, and mimic synchronous generator behavior with virtual inertia and droop control. All of this ensures a stable, resilient, and sustainable energy future. Let's summarize why grid-forming inverters are so important. First, they can replace traditional synchronous generators. GFI is able to form and maintain both voltage and frequency, just like a generator. Second, they enable high renewable energy penetration. This is critical in systems with high PV and battery storage penetration, especially in weak or islanded grids. Third, they ensure reliability and resilience. With black start and seamless transition capabilities, GFMI helps maintain stable power under all conditions. And finally, GFMI can mimic synchronous generator behavior. By using virtual inertia and droop control, it provides the necessary system dynamics to support a modern renewable grid. In short, grid-forming inverters are a key technology for the future power system. Inverter solution by PEC Technology. Thank you very much for your attention. If you would like to learn more about grid-forming inverters or power conversion systems, please feel free to reach out to us at PEC Technology. Together, let's build a stronger, cleaner, and more reliable power grid.